You are welcome to All Nations University, and this is the African Space Station Project or the African STEM Satellite Project. Now, the purpose for this project is to bring the basics of space technology to about 1 million African students. Now, why is that important? We know that currently the richest man, Elon Musk, is from the space industry and he is trying to rule the world, so to say, from space. And therefore, we think that if a student does not have these basics, no matter the career path or the discipline that they choose, they may limit their opportunities in the future, which they usually call the space future of the earth. And that is why All Nations University is bringing this opportunity for every student to know about space science. The project is called the African Space Station Project because we want to do the same thing as the International Space Station. And this project is a historic one because this is the first time we'll have students from all the 54 African countries on a single project. And this presentation is strictly 2 hours. So we want every student to pay keen attention as you take notes in this presentation. Thank you. We understand that some schools which are learning from this PowerPoint presentation may not have registered for the program or this project. We have a very simple registration form where you just have to type in the name of your school and the country. So we want you to do that because it is only by registering that you are officially recognized as being part of this project, and whatever benefit that comes with it, you shall have it. So we have this QR code on this screen that you are seeing. Please, you can take a picture of it or a screenshot of it. Then you can scan it using the QR scanner on your phone. It takes you to the registration form where you can register your school, your group, or as an individual. So those who have already registered, then you are good to go. Before the lecture begins, I would like to take just a minute to introduce ourselves properly. So this is All Nations University in Koforidua, Ghana, where we have the School of Engineering, and then we have the School of Business and the School of Allied Health Sciences. At the School of Engineering, we have Oil and Gas Engineering, we have Computer Engineering, we have Biomedical Engineering, then we have Electronics and Communications Engineering and Computer Science. We also have the School of Business, where we have Human Resource Management, Entrepreneurship, Accounting, Banking and Finance, and we also have a very vibrant nursing program. Now, the school is known for the engineering works that it has done, especially the All Nations University was the university that was able to design and launch Ghana's first satellite to space in 2017. Before that and after that, no other university has been able to achieve that. So that is a little about All Nations University. So these are the founders of the All Nations University, Dr. Samuel Donko and Dr. Rose Donko, doing amazing work in Africa. To end the introduction, The university is known for a lot of awards, like a lot. When you go online, you Google All Nations University, you see the awards that we've had, a lot from the even from the president of the country. All Nations University is one of the chartered private universities in Ghana. In Ghana currently, we have more than 100 private universities, but about only 10 of them are chartered as at 2023. Chartered means that they have been considered by the government as strong enough or having the facilities to be able to operate as an autonomous university. And All Nations University is one of the 10 out of the 100. This project was initiated by the Space Systems Technology Laboratory here at the All Nations University, which designed and launched Ghana's first satellite to space and a world-known laboratory. This project is conducted by Mr. Joseph Kwanzaa, who is the administrator, Dr. Anita Enchua, who is the head of operations, and I presenting today. My name is Ernest Tay Mate, and I am one of the 3 engineers who designed and launched Ghana's first satellite to space. All right, so now the presentation is about to start. And within these 2 hours, the All Nations University is bringing to you basic knowledge in satellite communication. And also, as part of this program, you are going to have practical skill in how to design a satellite receiver and how to operate or communicate with satellites in space. Now, let me say that the participation in this project is quite wide. The scope of participation, I mean. That means that we have people who already have some knowledge in this field and others who do not have any knowledge. But right from the onset, we said that the main focus or purpose of this project is to let everyone have knowledge. So therefore, in our presentation, we are going to begin from the scratch. And within these 2 hours, I want every student to take notes because it's very practical. At the end of this project, your school is going to have a STEM facility, all right? A facility which is a satellite receiver where your students can practice STEM by receiving data from satellites in space. Okay, so from year after year, batch after batch, this facility belongs to the school and students that come can practice with it. And by participating in this project, your school also steps on the road of becoming a spacefaring school, which I believe is a prestigious tag, okay, on your school among the competitor schools in your community. And this project will also deliver international collaborations because you are working with people from the other 53 African countries, okay? And in this project is going to serve as a rewarding leisure, which means that one of the STEM dreams that people have is to be able to communicate with astronauts and to ask them questions, okay? Astronauts in space. And that will be realized in this project, okay? And the last product is that you will be a part of this history. This project is a historic project and you are already a part of it. You will be captured, or your school will be captured in the media, documentaries, and whatever publications that happens. So we are going straight into the presentation and we are going to begin from the basics. Now, we are beginning from what is a satellite. What is a satellite? The word satellite is a Latin word which means a smaller body that is going around a bigger body. On your screen right now, you can see the smaller orange ball which is going around a big orange ball. So this smaller orange ball is a satellite, and the big orange ball around which the satellite, the big blue ball around which the orange ball is going, is called the primary. The primary. Please take note of that. The primary. Great. Knowing the definition of a satellite, we are going to answer the two kinds of satellites, which I know that a lot of you are already aware of. So we have the natural satellites and the artificial satellites. Looking at the narration here, you can see the moon going around the earth. So the moon is a natural satellite. The earth itself, together with its moon, goes around the sun, and therefore the earth is also a natural satellite. In higher classes of um, space science, you will learn that actually our solar system itself is also going around something, and even our galaxy itself is also going around another thing. All right, great. So we are going to answer what are artificial satellites and why artificial satellites. We always like to use illustrations to answer questions, okay, because we believe that illustrations are the best way to communicate what should be understood. Now, look at this photographer here who wants to take a picture of these five people, all right? Now, when he takes the picture, most likely we are only going to see this lady, the first lady, and maybe the head of the second guy. All right, so how is he going to take the picture of all five? So he devised a means of climbing something or increasing his height. So by increasing his height, when he takes this picture, most likely you are going to see all five. Okay, so what helped him? He increased his height. Look at this photographer who also stood on one of the tallest buildings in his city. Now, when he takes this picture, you are going to see a wide coverage of the city. Is that not it? So what if he stands on a mountain? Okay, you can see even wider. Okay, so what are we trying to say? By increasing your height, you are increasing your coverage. Now, I want us to answer the question, where is space? Okay, we are going to space. Okay, so where is space? Now, the definition of space should be by international agreement because of regulations. So, internationally, we should have a common definition for space. Now, space is any altitude or height 200 kilometers above sea level. All right, 200 kilometers above sea level. So, as you are listening to me right now and you decide to jump and you are able to jump 200 kilometers high, all right, you are a space object. But let me give you an idea what 200 kilometers actually means. Look at this illustration here. If you are able to jump only 3 kilometers, we may not be able to see you again, because by jumping 3 kilometers, you have actually entered the clouds and will not be able to see you again. So that is just 3 kilometers, all right? And airplanes, they fly just between 10 to 15 kilometers, just 10 to 15 kilometers. So we don't call them space objects, all right? Because this is just 10 to 15 kilometers. But space are, or space objects, they are objects that are 200 kilometers above sea level. Great. So if you begin to enter 200 kilometers above sea level, this is how you are going to see the Earth. All right. You see that by this height, this photographer is able to see a great percentage of the whole Earth at a time. So now, what is remote sensing? Remote means that you are at a distance. Just as in your homes, you have a remote control, and from a distance, you control your television. Sensing means to gather data. So, remote sensing means that you are at a distance and then you are gathering data. Now, look at what is happening on the ocean. This is what we know as the tsunami. Now, if this occurrence is about to happen and we are on land, how will we know that this is about to happen? So we'll just be there and the waters from the ocean will come and destroy us. But if we have a satellite there, okay, from a distance, it is able to tell us that this is what is about to happen. So satellites are used for remote sensing. Now, imagine this lady who wants to speak to a friend, but the friend is across a mountain. Now, when she speaks, okay, the friend is not going to hear because of the mountain. So they devised a means of letting these two guys, all right, okay, so let's say they are gossiping, okay. So these two guys standing on the mountain. Now, this lady speaks, and this guy will hear, and this guy will tell this guy, and then this guy will tell the lady what um she said. So by these two guys, they have overcome the obstacle of the mountain. So these two guys are acting exactly as a satellite. So we say that satellite is used for global communication. All right. So through a satellite, you are able to make a call from one country to another country, overcoming whatever obstacles, being it mountains and oceans between you. Okay, so satellites are used for global communication. So somebody will ask that, where are artificial satellites? We've heard about artificial satellites. You've just told us that they are used for communication, remote sensing. Satellites are used for navigation. They are used for meteorology, for broadcasting. Like we watch football, Europa, European Champions League. All right, through a satellite. But where are they? Okay. Now we are adding this slide to answer that question because I remember in 2017 when we launched Ghana's satellite to space, people were asking so many questions. Okay, so people could ask that, so where is the satellite? Did your satellite go to the moon? Did it go to the sun? Did it go to the Mars? Did it go to Mars? Did it go to another planet? And all that. So those questions made us to understand that people are not able to conceptualize what space looks like. All right. So we are talking about putting satellites in space, 200 kilometers above sea level. Now, you can see this illustration of the solar systems. The solar system, the planets are not they are not actually drawn to scale, but you can see the big sun here. All right. Now, the distance from the Earth to the moon, you can see the moon going around the Earth, right? The distance from the Earth to the moon is not a small distance. You see how close you see them, okay, as compared to the other planet, it's not a small distance. Not to talk of the next planet or even going to the sun, all right? So, satellites, okay, they don't just roam in space, moving from one planet to another planet and will go to the moon and back, all right? It's not like that because it is a very far distance. So, about 99% of satellites in space, they are just within this red ring, all right? They are just between this they are just within this red ring. So don't think that when we launch a satellite to space, it is moving from planet to planet. Okay, the planets are very, very far, and that is why we have special missions where a satellite will land on the moon, or a satellite will land on Mars, or a satellite will go around the sun. These are achievable, but they are special missions and they are very costly, like very, very costly. So the normal satellite that is launched to space is just around the Earth, okay, relative to the distance from the Earth to the moon or to another planet. Great. So how do the satellites get to space? How do they get to space? Okay. Now, currently, the most reliable way for you to put your satellite into space is by using the rocket. Okay. Other inventions and research is being done, but currently the most reliable way is by using the rocket. Now, let's concentrate on illustration A here. Illustration A. We have an upward moving force in the red, and we have a downward moving force in the blue. Now, if these two forces, okay, their magnitude is comparable and they act on the same object, what will happen is that the object will have a resultant force in this direction in the green line. All right, so just imagine what is happening. Okay, an up force and a down force. When you study vectors, you realize that there will be a resultant force in this direction. Okay, because these two forces are acting on the same object. Now, let's come to illustration B to answer how satellites get to space. Now, we know that we have what we call the Earth gravitational pull, which Newton discovered that two bodies are constantly attracting each other towards themselves. All right, so two bodies are naturally attracting each other towards their center. All right, so now the Earth has this natural force, okay, attracting everything towards itself. Now, we also we want to escape this force and go to space 200 kilometers far from the Earth, at least 200 kilometers far from the Earth. So that is why we use the rocket. So the rocket is made up of gases such that it is giving that propelling force, okay, to escape the Earth gravitational pull to go to space. So the rocket has that upward force, okay, upward movement. Now, it is shot very high, okay, with a very high velocity, and it's going up. But remember that this Earth gravitational pull is not cancelled. So that force is still acting on the rocket. Now, the satellite that we want to put into space, it is actually put inside the rocket. Okay, so when it gets to space, we have a process called separation to separate, and the satellite will come out of the rocket. Now, when these two forces that you are seeing are acting on the rocket, when the rocket gets to a certain height, it will take this resultant force and direction. So when you study the animation very carefully, the animation you are seeing, you see that the satellite, it moves up, all right, and then when it gets to a certain height, it takes a natural path going around the Earth. So now, we would like to answer this question. People ask us that what kind of motors are your satellites using in space, or by what engines is it moving in space? But the satellite does not use motors to move in space. It does not use engines to move in space. So satellites go around their primary, and in this case, the primary is the Earth. Satellites go around the Earth by virtue of the balance of forces acting on it. So it had an initial force from the rocket, and the Earth gravitational pull also acting on it will give it that natural force to go around the earth. So it's like you want to spin a ball, okay? You have a ball on the ground and you spin it. So when you give it that initial force, okay, and you leave it, it will continue to just spin. So that is what is happening here. So satellites go around the earth by virtue of the force that is acting on it, causes it to remain going around the earth. Great. So the path which the satellite takes around the earth is called the orbit. The orbit. ORBIT. Now we are learning about satellites, all right? So I want you to take keen interest in what we are doing and pay keen attention, all right? So please take notes. The path that the satellite takes around the earth is called the orbit. And here I am illustrating the orbit with these colors, green, yellow, and red. Okay, so it doesn't mean that when you go to space you see a green line or you see a yellow line and then a red line. Okay, these are imaginary lines. Now, not all satellites are in one place, so don't think that all the satellites are in one room in space. Okay, so satellites are in different heights or altitudes above the earth. So there is a reason why one satellite will be put very close to the earth and why another satellite will be a little far, and why another satellite will be very far. We'll soon learn about that. So there are satellites that are very close to the earth, and that orbit is called low earth orbit. Okay, so any satellite which is between 200 and 2000 kilometers above the earth is said to be in low earth orbit. There are satellites that are also a bit higher, between 2,000 and 20,000 kilometers from the surface of the earth. So they are called satellites in medium earth orbit. Okay, example, our GPS satellites, okay, they are in medium earth orbit. And we have satellites that are very high. Okay, there's a reason why they are put very high, and those satellites are in high earth orbit. Okay, great. So these are the three basic types of orbits. We have other special types of orbit, but these are the three basic types of orbit: low earth orbit, medium earth orbit, and high earth orbit. And there are reasons why a satellite will be put close or a satellite will be put very far from the earth. All right, thank you. We are moving higher. We are going to look at operating satellites. Operating satellites. And here we are going to talk about how to communicate with satellites and how satellites are tracked. Okay, and most important of all is that you need to know how to do these things for you to be able to do it in your schools. Great. So we spoke about the space object or the space station, like the satellite, all right? And we also have earth stations, okay? So whatever the satellite is doing in space is gathering data. It has to send it to us for us to benefit us on the earth. So we need to have earth stations which are able to receive these signals from space. Example, we have this ship or this vessel on the ocean, all right? It needs some navigational data like GPS to be able to navigate its way on the ocean. So it is receiving data from satellites, from the GPS satellites, and therefore it will have an earth station. Okay, and students can also become an earth station. All right, so I'll put a picture of my students who were collecting very important data from satellites in space. So we have the space station and different kinds of earth stations. Now, about operating of satellites, okay, if you have this thing that you are seeing, this device that you are seeing on your screen, if you have it in your house, okay, this is a satellite television, then I am glad to inform you that you are already operating a satellite in your home. Okay, so this device that you see okay, it's an satellite station, is an antenna that receives signal from a satellite in space. Therefore, you realize that in your homes, you have a ground station, right? A satellite receiver where you have an antenna, you have the radio receiver or the decoder, as we call it, and you have the signal display. So this is actually a complete set of a satellite receiver. However, with this system, all that you can do is to watch television, right? Or to listen to an FM radio. But then in this project, we are interested in doing other STEM experiments, okay? Like talking to astronauts on the International Space Station. So we are now going to look at how to develop our own satellite receiver to be able to do that. Play. Now, if you were at home when the technician came to install your satellite television, you realize that he went outside and installed the antenna, okay, and pointed it to the sky. And if you were at home, you would have realized that he had this device with him. This device is called the signal analyzer, okay, the signal analyzer. Now, you would have noticed that he points the antenna to the sky, he will tilt it at an angle, and then he will come back to the signal analyzer to check something. Then he will go back to tilt it. Now, if you had asked him that, what are you doing? He would have told you that he's checking for signal strength, for signal strength. Okay, so he's pointing the antenna to a satellite in space, okay, and he's checking for signal strength. So let's learn how this applies, okay. Great. So we are going to the next slide. Now, satellite communication is a line of sight communication. This is a technical word, a line of sight communication. But let me explain it in the simplest way. What is line of sight communication? Line of sight communication means that if we have to talk, like you see this guy, these two guys, okay, if we have to talk, then we have to be looking at each other. Okay, so don't turn your back to me when we are talking. It's not possible. So if we have to talk, for me to receive your signal, okay, so talk is sound signal, all right? So if I have to receive your signal, okay, then we have to be looking at each other. The satellite transmits radio signals and your antenna receives it in the house, but it is also a line of sight communication. So your antenna has to be looking directly towards the satellite, and that is what the guy was doing. Now, let's see how this works. There's what we call field of view, field of view, field of view, field of view. What is field of view? You know that the way our eyes are made, when somebody stands behind you, when somebody stands behind you, you will not be able to see the person. Is that not it? Why? Because your eyes have the maximum angle it can look at. All right. So that if somebody stands outside the angle that your eyes can see, you will not be able to see the person. That is what we call the field of view. Now, anywhere that you stand on the earth, you have a field of view. So we are indicating this field of view with this ash triangle, sorry, with this ash triangle. So you see that this guy, wherever he's standing, he has a field of view. And your home's satellite television, the antenna, also has a field of view. Great. You see that the satellite in space also has its field of view. With this illustration, the field of view of the satellite is indicated by the green triangle. The field of view determines the coverage of the satellite on the Earth. All right, the field of view determines the coverage of the satellite on the Earth, because it is only when you are in the field of view of the satellite that you can talk with the satellite. So to say, I'm using the word talk or hear, it is non-technical, but it's just for you to understand. Now, that coverage of the satellite on the Earth is called the footprint of the satellite. The footprint of the satellite, all right? So the satellite has a footprint on the Earth, okay? So it is only those antennas within its footprint that can receive the signal from it. So this is what the guy was doing. What he was doing by tilting your antenna is he's trying to align the field of view, okay, of your antenna to the field of view of the satellite in space, so that it is only when these two field of view intersect that you'll be able to receive a very good signal. Now, let's assume that the guy couldn't really tune or tilt the antenna well. So your antenna is misaligned. In this illustration, the field of views are not intersecting. So there is no way your satellite television can receive signal. So all that you see is no signal on your screen. All right. So in this case, the field of views do not intersect. So there is no signal. Let's look at this scenario where there is a little intersection between the two field of views. So in this case, you may receive some signal, but it's a very weak signal. So let's say that the signal that is being sent is like 10 because of the little intersection. So you are receiving 2 out of the 10. So your signal will be very, very weak. Great. Now let's go back to this illustration. The satellites are moving in space. Is that not it? Now, when you look at this animation, you realize that the satellite that is closer to the Earth, the one in the low Earth orbit, is moving faster than the satellite in high Earth orbit. Is that not it? So the closer the satellite is to the Earth, the faster it goes around the Earth. So the higher you go, the slower you become. But why is it that the satellites that are closer to the Earth are moving faster? Let me explain it to you. It's like you put two magnets together. The closer they are, the greater the force of attraction between them. So Newton said that there's a natural force of attraction between two bodies, and it depends on the distance between them. The closer they are, the higher the force between them. So the satellite in low Earth orbit, being closer to the Earth, there is a higher force of attraction to the Earth than the satellite in high Earth orbit. So that force of attraction is actually what is causing it to move faster around the Earth than the ones in the higher orbit. Going around the Earth is called revolution. There's a difference between revolution and rotating. Rotating is like you spin a ball. The ball is at one place, but it is going round. Okay, it is spinning. That is called rotation. But revolution means that you are actually moving around. So now, when you go high and high and high, there is a possibility that the speed at which you go around the Earth will be the same speed that the Earth is rotating. Now, look at this animation here. Concentrate on this illustration A. All right. The Earth is rotating, is spinning. The satellite is revolving. The Earth has a speed by which it rotates. Now, we took the satellite so high that it got to a certain place that the speed at which it is revolving around the Earth is the same speed at which the Earth is rotating. So now, if this antenna and this satellite are looking at each other, they will remain looking at each other. It's like you are talking to somebody and you are walking at the same speed. There's no way you misalign. So you seem to be consistently looking at each other. All right. So that kind of orbit where the speed of the revolution of the satellite is same as the speed of the rotation of the Earth is called a geostationary orbit. Geo means Earth and stationary means just stationary. All right. So that is what is happening in your homes. The satellites that your home antenna is receiving from, these satellites are in geostationary orbit. So from the day that your antenna is pointed to the satellite, there is no misalignment between them. Your antenna is on the Earth and the Earth is rotating with it, but there's no misalignment. That is for illustration A, right? But let's look at illustration B. In illustration B, we have the satellite in low Earth orbit that is moving very, very fast. Typically, a satellite in low Earth orbit, like the International Space Station, which some of you see in movies, is a very big satellite. The size is like the size of a football pitch, and we have astronauts living on it, okay? Now, that satellite is in a low Earth orbit, it's moving very, very fast. Okay, a typical satellite in low Earth orbit takes about 90 minutes to go around the Earth. 90 minutes. While the satellite in geostationary orbit, of course, will take 24 hours to do so. The satellite in low Earth orbit takes 90 minutes. So you can see that it's moving very, very, very fast. Now, because it's moving very fast, for that satellite to cross your country, it takes just between 5 to 7 minutes to just fly over your country. Okay, because it's moving very, very fast. That is the satellite in low Earth orbit. But what happens is that most of university satellites, or the satellite that we are going to receive their signal, unfortunately, they are in low Earth orbit. So those satellites, they are moving very, very fast. They are not like this, the satellite that our home antenna is receiving from, right? They are in low Earth orbit. They are moving very, very fast. So that is why we need to learn about satellite tracking. Example, in this project, we are going to communicate with astronauts on the International Space Station. And that International Space Station, because it is very close to the Earth, is in low Earth orbit, somewhere around 400 kilometers. It is moving very, very fast. So we need to learn how to receive signals from satellites that are moving very, very fast. Okay. A typical satellite in low Earth orbit moves at a speed of somewhere 7 kilometers per second. 7 kilometers per second. You may not understand what 7 kilometers per second means, all right? But 7 kilometers per second is, the speed of a gunshot. When somebody shoots somebody, the bullet, the speed of a bullet is about somewhere between 1.7 to 2.5 kilometers per second. But we are saying that a satellite in low Earth orbit, okay, we have many satellites, more than thousands of satellites in low Earth orbit performing different functions, and they are all moving very, very fast in space, okay, about 7 kilometers per second. And that is like 2 or 3 times the speed of a bullet, all right? And in this project, those are the satellites that we want to receive the signal from, all right? So now we are moving higher. Okay, it's going to get more interesting. Okay, we are going to talk about satellite tracking. Tracking satellite in low Earth orbit. In your homes, there is no tracking. Okay, because the antenna and the satellite, okay, whether it's DSTV, they are looking at each other forever. But in your case, the International Space Station is not looking at you forever. It is moving very fast, and you want to communicate with the astronauts. So let's go into satellite tracking. Now, from this animation, you see that the satellite is moving in space, okay, and you have your field of view indicated by the ash triangle. So now, there is a time that the satellite enters your field of view, and there's a time that the satellite will leave your field of view because it is moving. Now, the time that the satellite enters your field of view is called acquisition of signal time. And the time that the satellite will leave your field of view is called loss of signal time. I repeat, the time that the satellite enters your field of view is called acquisition of signal. So what is acquisition? Acquisition is to acquire, to collect. So like we said, it is only when the two field of views intersect. So the only time that you can receive signal or data from the satellite is when it is in your field of view. So there's a time that it enters your field of view and there's a time that it leaves. So the time that you will be able to acquire signal from the satellite, that is when it enters your field of view, that time is called acquisition of signal time. So it spends some time in your field of view and then it leaves. So the time that it leaves your field of view is called loss of signal. Okay, so here it's like you are losing the signal. So loss of signal. Like a typical satellite in low Earth orbit, like we just said that it's moving very fast. Okay, the time between AOS time and LOS time is just between 5 to 7 minutes. All right, so please bear this in mind. Depending on your position on the Earth, your longitude and latitude, as the satellites are flying in space, they come within your region or they fly over your country, they enter your country, okay, at a certain time and then they leave. So the time that they'll enter as flying over your country is called acquisition of signal, and the time that they'll fly past your country is loss of signal. Now, we have also established that the satellite also has its field of view. Is that not it? So now, in this animation, you see that it is only when the field of view of the field of view of the satellite is within the field of view of where you are, your location on the earth, that is the time that you can communicate with the satellite. So now, these are the two important things that you need to know about any satellite when you want to receive from it. So let's say that today in your school, you want to communicate with the astronauts on the International Space Station. So, what time are you going to communicate with them? All that you need to know is the AOS time of the ISS today, okay, over your school and the LOS time. So, it is between this time that you'll be able to establish communication with them. So now we are moving a bit higher. What will I use to receive the signal from the satellite? Okay, now I know that the satellite is passing. So what am I going to use to receive the signals from the satellite? Now, in your homes, you have the antenna. Is that not it? So the antenna is that device that is actually receiving the signal from the satellite. So it is the antenna that is pointing to the satellite. The satellite is broadcasting the signal, and these signals in codes, they are hitting your antenna, and then it passes through your antenna is like the collector that collects the signal. I'm using non-technical words. It's like the collector that collects the signal, and then it it passes it through the cable to the decoder, and then you see it on the screen. So what is a satellite signal? What is a satellite signal? Somebody may be asking that. What is a satellite signal? Okay, so for us to be able to answer the question, what is a satellite signal? We need to understand electromagnetic waves. Electromagnetic waves. So what are electromagnetic waves? I know that some of you may have done it in your schools. For some, maybe it's not part of your syllabus yet. But then we need to know about electromagnetic waves. So two words sound familiar here. Is that not it? Electric and magnetic. Electric and magnetic. Now, let's focus on illustration A. Illustration A. We learned about the atom, atom, where we said that the atom is the smallest unit of every substance. All right. So when you go higher in your education, all right, and you do applied physics and you do quantum theory or quantum physics, you will get to realize that that definition is not quite accurate. But now, at your stage, yes, the atom is the smallest unit of any substance. And then we learned that the atom is made up of electron and nucleus. So in this illustration, the electron is demonstrated by the yellow cycle, and then the nucleus is that the black cycle, right? Okay, so the electron is a yellow cycle and the nucleus is a black cycle. Now, when the electrons, when they receive energy, they are excited. It's like some of your friends, when they receive money from their parents, nobody will sleep in your dorm. They are excited, they'll be moving around, okay? So when the electrons receive energy, they are excited, okay? And then they begin to move. So when they are induced with energy, they begin to move. Now, that induction of energy, all right, that energy is in the form of electromagnetic energy, okay, producing electromagnetic waves. Now, so this electron has received some energy and is moving. Now, let's look at illustration B. Illustration B is the same as illustration A, but we have just divided the cycle into two. So we have the upper one called the positive cycle, and then we have the lower one called the negative cycle. So when an electron receives energy and is excited, it moves between the positive cycle and the negative cycle. Illustration C is the same as B, but we have just joined these two semicycles. So you see that the electron moves from positive cycle to negative, positive to negative. Now, you may have seen that electromagnetic waves are drawn like this, okay? This curvy thing, all right? They are drawn like this, but this is the reason why they are drawn like that. So the electron is moving between positive cycles and negative cycles. Now, there is a characteristic of electromagnetic waves called their frequency. And their frequency is dependent on the amount of energy that they received. Now, let's look at atom yellow and atom green. You realize that the electrons in atom green, they are moving faster than the electrons in atom yellow. Why? Because they received more energy. They received more energy. So if we come back to how we draw the electromagnetic wave, you see that in the atom yellow, because they are moving very slow, in 1 second, how many cycles was it able to go? So this is 1 and 2, okay? But for the green, because it received high energy, okay, it's moving faster, so it was able to complete, let's 1, 2, 3, 4. It was able to complete 4 cycles in 1 second. Now, this is what we call the frequency of a wave. Frequency of a wave. The frequency of an electromagnetic wave is measured in the unit called hertz. Hertz, which is the name of the scientist who discovered that electromagnetic waves can be produced and they can travel in space from one place to another place, and they can be made to carry information. So now, what is the frequency of this yellow wave, all right, this yellow atom wave, so to say? Frequency is measured as the number of cycles per second. So this one was able to complete 2 cycles per second. So the frequency of this is 2 hertz. The frequency of B, because it's able to complete 4 cycles per second, its frequency is 4 hertz. So frequency is measured in hertz, okay, and it gives an indication of the amount of energy that this electromagnetic wave is carrying. So electromagnetic waves, they are graded according to their frequencies. So we have what we call HF. HF is high frequency, VHF is very high frequency, and UHF is ultra high frequency. So I can say that this radio wave is in the VHF band, okay, that means that it is very high frequency, or it's in the UHF range, that is ultra high frequency. Now, so that means that when we say kilohertz, kilohertz actually means 1,000 cycles per second, all right, 1,000 oscillations per second, because kilo is 1,000, megahertz is 1,000,000 oscillations per second. So when I say 400 megahertz, 400 megahertz means 400 million oscillations per second. So that is the amount of energy that that wave is carrying. Gigahertz is 1,000,000,000 oscillations per second. So when I say that a wave is 1 gigahertz, that wave is carrying a higher amount of energy than a wave that is kilohertz. All right. So now, understanding this, what is signal? A signal is an electromagnetic wave that has been made to carry some information. Okay, information can be sound. Example, sound is an electromagnetic wave, but it is encoded to carry information. Like what I'm speaking right now and you are hearing, because the electromagnetic wave that is coming into your ears, okay, is intelligent. All right. So, example, Bluetooth. Bluetooth is an electromagnetic wave on a certain frequency. All right. So, pictures are converted into that electromagnetic wave and they are transported through space or through the atmosphere. Your eyes cannot see it, but then the electromagnetic wave was made intelligent. And what was that intelligence? That intelligence is the picture you are transferring from one phone to another phone. So now in your homes, your antenna is receiving electromagnetic waves from the satellite, okay, but those electromagnetic waves are intelligent, and that intelligence is what you see on your screen as whatever thing that you want to watch on the station.